So priors or probability of the dog and probability of cats, right? So we look at this. We have 1, 2, 3, 4, 5 dogs, right, out of 8. So probability of dog is 5/8, cat is 3/8. Dog given by Brown. So let's look at Brown. 1, 2, 3. And there's one dog, so it's 1/3. Cat given Brown is 2/3. All right, so that's the 2. And now the last one is about naive Bayes. Right, so we're here, right? So according to naive Bayes, we're going to compare this and given cat P of meat given cat P of yes given cat, compare against P of dog, P dog given wait, black given dog, probability of meat given dog, probability of yes given dog. So cat, let's do the top one. 3/8 times cat and black. So there's 1/3 times meat for cat is 1/3 as well. And yes, given cat, which is 1/3 also. And now let's look at dog. So dog is 5/8 times black dog. Black dog is 1, 2, 3, 4, 4, 5. Meat dog 3/5. And yes, dog is 3/5. So comparing them, right? Which is what 1/9 times 8, 1/72. This one 9/50. So dog has higher probability. So this one, the answer is a dog. All right. Right now, let's talk about this lecture. So today's lecture is about like unsupervised learning, especially clustering. So we're going to talk about 2 techniques. One is k-mean clustering, and the other one is Gaussian mixture model. So what is unsupervised learning? So unsupervised learning is a technique where you want to learn some patterns or structure in your data, right? So you're only given your data, which is X, but no labels at all, right? So what can you do with it? Maybe like customer or product segmentation, or like identifying speakers in a recording, or like learning insights from the data, or like group customer complaints, right? So let's talk about one simple example, maybe like this, right? So maybe you did some poll, right? And you ask people to fill some poll about like whether they're loyal to like a phone brand or not, right? And how sensitive they are to like price changes to the phone brand, right? And when you plot them on two axes, right? The question is like, oh, can you identify groups of customers, right, from this uh, data, right? And this one is very simple, right? You by looking, right? By looking, you can say, oh, there's three groups, right? Very simple, straightforward, right? But in the real world, so this is a real project that I did 10 years ago also. So this is real estates in Thailand, like condo, houses, or like share home or whatever, right? So each dot represents a place that is on sale, right? And this data come from like a real estate listing website. So there's a website that lists like 5,000 real estates at the same time, right? So you have like 5,000 data points, right? And what we're doing, right, in this website, where since this is like 10 years ago, during that time, there's no like PDPA or GDPR yet. So you can track cookies very easily. So what we just do is just, okay, let's track the cookies of the visitors, right? And see like, oh, visitor one, they visit the project 1, project 4, project 5, right? Visitor 2, look at project 4,000, right? So we just look at the visitors, right? And we just want to see like, oh, what are like the segments, customers, or like what are like the segments of like real estates in Thailand, right? Because we might assume that, oh, the people, right, who look, right, if the same group of people look at a particular project, right? For example, here, right? If you notice like, oh, project 1 and project 5 has very similar patterns, right? Have very similar patterns in the people who look at the project. So maybe project 1 and project 5 has something that we can analyze, right? So we want to group projects that garner similar interests, right? And in this case, right, each project, right, is represent as a vector, right? So your input feature is this. It's a 1 million dimensional feature, right? Just binary feature of 1 million people for each project, right? So in this case, it's very different from here, right? From here, you can just look by eye, right? But here, if you have a metrics of like 4,000 by 1 million, you definitely cannot look by eye, right? So we need some tool to help us like cluster these projects together, right? So, well, let's look at the results first, and then we'll talk about the technique later, right? So this is the results of the clustering. If you just cluster by like views, right? It turns out that, oh, even though you cluster by view, you get a very location-based cluster, right? In my input, I didn't input in any like location information at all, right? But my clustering just turns out to be location-based, right? Which is interesting, right? Because like when people shop around, right, shop around the place they look, right, this website, they might have like some tendency to look for uh, zones and things like that, right? And here, you might notice some particular shape here. So in the middle, there's this shape, which is a bit strange, right? Anyone know what this shape represents? This is 10 years ago. BTS line, the first two BTS line, right? During that time, there are only like two lines, and it's very short, right? Much shorter than now. So there's like the east-west line, and there's this the one that go up north, and there's this like Siam is here. So this means that there's like a certain demographic of people that just don't care, right? They don't care where they live as long as it's close to BTS, right? So that's interesting. And actually we can look the entire Thailand, right? This website has information for the entire country, actually. So we can look at other zones. For example, here, this is Chiang Mai. So Chiang Mai is divided into two groups. One is the inner city, right, where there's pubs and bars, right, in the inner cities and hostels, right, which is very different compared to the suburbs of Chiang Mai, right? Or here, so you have Pattaya, right? And anyone know what this is? This zone is? What is this zone? Hua Hin. Hua Hin. So Pattaya and Hua Hin has the same demographic, right? Because they're pretty much like beach resorts, and very close to Bangkok, as in like it would take around the same time to drive there, like 3 hours. This is 10 years ago. Nowadays, people don't want to drive this way that much, right? With all the construction and all the accidents. But this is 10 years ago, right? When the accidents aren't that frequent, right? And it's a different demographic, right, between Pattaya and Rayong. Rayong is more like industrial complex, right? So it's more like engineers or workers, right? That goes there. But this is interesting, right? When we found this 10 years ago, and we discussed with like real estate experts, right? They're very like excited from this finding, because now they can like advertise, right? Advertise their condominiums in Pattaya at Hua Hin and vice versa. Usually advertisement in real estate are more location based, right? But this shows that, oh, actually there are like substitutes, right? We call it substitutes item that can be far away from each other, right? Another cute thing is here. So there's this northeast of Bangkok, and the southeast of Bangkok, they have the same demographic, but in the middle, it's different, right? Anyone know why the middle is different? This is the east side of Bangkok. Was on the east. Now here you see, notice like the airport, right? And there's the red line, right? The airport rail link is there. So this zone is more developed compared to the north and the south, right? But if you compare like, oh, the north and the south has similar price range, and they also take the same time you want to drive in to like downtown Bangkok, it takes very similar time, right? So they have the same demographic, right? So that's cool, right? So this is I hope this gives you an idea of like unsupervised learning or clustering, that we start out with something that like just some data, right? And we cluster, right? And then we try to like analyze, right? Analyze what we get, right? And then we act on this insights. For example, oh, okay, so usually real estate developers, they focus on certain regions. Let's say, oh, they might build houses. They might build houses here in this zone, right? They might build houses in this zone because they know, like, oh, people who come to this zone, what is their demographic, right? So they can like, okay, we should build this kind of house using this kind of materials and things like that, right? And they're very comfortable in this zone, right? But if we can tell them that, oh, actually, you can do the same thing here, right? That's very valuable to them, right? So the idea of unsupervised learning, which is about like gaining insights from data, right? People you should think about like, oh, when we talk about unsupervised learning, we're like, oh, okay, we only need X, right? We only need X. We don't need to do anything. We just put data into the algorithm and we get something out of it. Actually, it's no, right? We put data to the algorithm and then we analyze the results, right? Analyze the results, look at the outcome and try to come up with like insights, right? That's where the human supervisions come in, right? We're not supervising on the labels, but we're supervising on the insights level, on like what action the business will do next, right? So in a certain in a sense, so unsupervised learning is actually harder to use in the real world because like it requires some imagination on the people who use it, right? Oh, how do you analyze these results when you throw in data, right? When you throw in data and you get something like this, right? How do you act on this insight? So this is something to keep in mind. All right, so that's the use case, right? But how do we do it, right? How do we do it? So what we're going to discuss first is our first algorithm, which is k-mean clustering, right? K-mean clustering. So k-mean clustering tries to cluster this data, right? This data that I just showed you, right? But in this, like, if we just look at here, right, it's very simple, but in this data it can be very hard, right? How can we do this, right? So let's think about an easier problem, right? So if I already have clusters, let's say, oh, I have a blue cluster, green cluster, a red cluster, and then I have a new data point, right? And I can ask like, oh, which cluster should I assign this point to? Right? Which cluster should I assign this point to? This looks more straightforward, right? So we can say, okay, this thing, right, is very close to the blue group, right? So I would say that this thing is blue, right? So we can maybe measure distance to points, right? To points in the data, right? And look at which one is the closest. And we say, okay, the closest is our answer, right? And this is called nearest neighbor classification, right? We look at the closest point. And in this case, that if we have this case, right? Oh, our cluster looks like this now. We have like a red point here, right? And we have the item that we want to answer here, right? In this case, maybe we want to do some kind of voting, right? Oh, we look at the three closest points, right? Three closest points, which is blue, red, and then we vote, right? We vote. They say, okay, this is blue, right? So this is called K nearest neighbor. That is, oh, we look at the K nearest points, and then we vote, right? And we vote the according to like who are the K nearest ones, right? So this for example, this is an example of K equals 4. Like we take the voting from 4 neighbors and then assign, right, blue, right? So the voting here can also be weighted. That is like, oh, okay, this has a distance of 2, this has a distance of 3, this has a distance of 4, this has a distance of 5. I can vote by distance as well. Like the nearer one has more votes. Right? There's another thing that we need to think about that is like, oh, when we talk about nearest, how do we measure nearest points? So we can either measure by distance, for example, Euclidean distance, right? Euclidean distance, or we can measure cosine similarity. That is, we have like, if we have two vectors, right, the cosine similarity is the dot product, right, divided by the norms. So for example, that if I have a vector x1 and x2, right, the Euclidean distance is this distance, but the cosine similarity is the angle. Okay. Right, so this is k-nearest neighbors, right? Just talk about how do we assign uh how do we assign a label to a point, right? We can also do a variant of this by, instead of comparing to the points, right? Instead of comparing to the points, we can compare against a representative of a cluster, right? So let's say, okay, from this cluster, right, I have this representative. From this cluster, I have this representative. From this cluster, I have this representative, right? So this representative, we can call it the centroid, right? Centroid, the centroid of the cluster, which is just the mean of all points, right? All points. That's the centroid, right? So when we compare the nearest, we just compare nearest to the centroid instead, right? So here, right, if we do this, right, this algorithm becomes more efficient, and that's what people use for the k-mean clustering algorithm. So in k-mean clustering, we're going to start by randomly picking k centroid, right? So we're going to pick data points. Let's say, oh, okay, this one will be centroid 1. This one will be centroid 2. This one will be centroid 3. We pick k points to be our centroid, and then we assign each point to the centroid. So here, this one will be 1, right? This one probably 2, right? This one is 2, and this one is 3, right? So this is step 2, assign the points to the centroid. And then step 3, we compute the centroid. So okay, here, if we compute the average, it's here. Here's the centroid. If in this group 2 here, the average is here. Group T3, the average is here. All right. So we update the centroid and we repeat the steps. All right. So this is k-mean clustering, or this is like an example animation. We start with points, right? No assignment at all. Randomly select centroid, assign the points. I assign the points. Update the centroid according to the middle point, right? So the middle point, this is the middle, so it's here, right? The centroid is here, right? So update the points, update the assignment, we assign the points again, update the centroid, right? We keep repeating these steps until there's no change in the assignment. So the algorithm of k-means is very simple, right? But the difficulty is actually about, okay, how do we pick the number of cluster, right? Because in k-means, we have to specify this k in advance, right? For example, in my real estate clustering example, how do I know how many groups are there? Right. So what we did is just, okay, we just pick a magic number. But okay, I will only do 60 group because I will have to look at each of them, and I don't want to spend too much time to look at each of them. So I only have 60 group, right? So it depends on your application, right? So if you want to extract insights, right? It's the amount that you're willing to work with, right? Or if you do like customer segmentation, for example, right? You do customer segmentation to create persona to develop some product, right? So if you want to develop products, right, you might have like, okay, I will probably develop 5 products. So that's your K, right? You group into 5 customer types. Right. So that's one way, right, to think about K. Look at the requirements, either from like how you're going to use it or your business, right, and pick your K. Another thing about K-mean clustering is when you do this, you're not guaranteed a good result. For example, if you pick this starting point, like, so you start here, 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 and you pick this starting point and you do K-mean clustering, you might end up with this answer, which is one group here, one group here, one group here, one group here. Right. So a bad starting point might lead you to a bad clustering. Right. So to deal with this, try starting at different points. Right. So you randomize different starting points and then pick the best one. Right. So that's the caveats that you need to think about when you're going to apply K-means. Right. Another thing is that in K-means, it has implicit assumption. First is the data points are pretty much going to be a circle, right? Going to be a circle in the feature dimension, right? So if you like have data sets, maybe like this. So I call this Mickey Mouse data set. So it has like a ear, right? And there's a big circle here, right? If you do clustering in this one, right, you will get this, right? Because K-means assumes that every cluster has the same variance, and they are all circle, right? But this one, the variance are smaller for the years, right? But in K-means, they will say, oh, every cluster has the same size, right? So that's the one of the assumption in K-means. Right. So this is another example of like how if you start at 2 different starting points, you can get different outcomes. Right. And here, right? So how do you know which outcome is the best? Right. If you do like two clustering, right? One with another different starting point, right? How do you know which one is better? So in clustering, there's several metrics that you can use. So scikit-learn has like a bunch of metrics that you can look at. So let's look at it real quick. So like, oh, there are so many metrics, right? And there's like supervised evaluation. That is, you have some labels, some ground truth labels. And there are unsupervised evaluation. That is, you don't have any ground truth label at all. Okay. So that's pretty much the consideration when you want to pick metrics, right? But these metrics, I wouldn't recommend you to rely on them that much. In practice, like I said at the start, right, the goal of clustering is to gain insights. I can cluster something, get some results, and I can maybe, I get some insight from this cluster. I can cluster it again and get another insight, right? So it doesn't really matter like which one is the best, right? As long as you get what you want out of it. Another technique that people usually talks about when selecting K is what they call the elbow method. The elbow method. So the elbow method will look at this number, which is how much your clustering is explaining the data. What is it? So let's look at the example first. So here, let's say, I have a cluster of 1. What does this mean? It's just one big cluster, right? One big cluster. If I have a cluster of 2, it might look like this. Cluster of 3 looks like this. Cluster of 4 looks like this. So this fraction of explained variance looks at, well, is the denominator is the all data variance, which is just the variance of the data, right? This is the variance of the data. And then it looks at how the each centroid, right? How each centroid is spread out from the mean of the data, right? So this is between cluster variance that talks about, how are the cluster difference, right? How the cluster are different. As you can imagine, like as we go, k become larger and larger, right? Each point. So the extreme is what? K equals number of data points, right? The extreme is we have the same cluster as the number of data points. So each data point becomes its own cluster, right? If we compute this value, it's pretty much the same as the variance, right? If each point becomes its own cluster, this value, right, which is talk about the centroid to the mean of the data, right? Since if each data point is its own centroid, then this value becomes the same as the all data variance, right? So this fraction of explained variance talks about like, when you divide the data into smaller and smaller clusters, how much is the variance of the data captured in the cluster itself? So you plot it, right? You start with some small value, and as you increase the number of k, this value will be larger and larger and larger until it hits 1. It hits 1 at k equals the number of data points, right? But what we want is where the trade-off between increasing k and increasing this variance explained. As notice how like at the start, right? At the start, when you increase k, this value increase very quickly, and as you go along, the slope becomes smaller and smaller and smaller, right? So your gain for each k becomes smaller. So you're looking at a point where this trade-off, where there's like a nice trade-off. So if you like consider like this is like an arm, right? An arm. So there's an elbow here, right? An elbow here. So this look at like an arm, right? And there's an elbow. So you look at, so this is like by eyeballing, eyeball, like, oh, okay, this point looks like a nice trade-off between increasing k and increasing the variance, right? So you pick the k value according to this plot. That's why it's called elbow method, right? So that's one way that people use in academia, at least, for determining k, right? But like I said, I don't recommend this method that much. Actually, I don't recommend this method at all. But I just mentioned it here because it's probably the most commonly taught about, right? So if you look at the books or look at like any tutorial, it will talk about this technique. But I'm very against this technique in general. Other more recommended technique is, for example, like, oh, okay, you have some cutoff. Let's say, oh, I want 95% of the variance in the data, and you have a cutoff here, and you plot that same plot, and you pick the first k that exceeds this value. Right. So this is at least like it has some like meaning in that, oh, okay, you're trying to cluster to capture this much variance of the data, right? It has some meaning that is more grounded than this elbow thing. Or you look at the downstream results. For example, maybe you cluster, right? You cluster to train some customer segmentation model for recommendation system, right? So what you do is you measure accuracy at the recommendation system level. So you measure the performance at your target task, right? And your clustering is more like an intermediate step, right? So you don't measure the performance there, but you measure the performance at the end, right? You don't care about the intermediate step.
อาจารย์ครับ can I ask a question?
Yeah.
Oh, sorry, what does the variance mean here again? I think I forgot. What does the variance
This
indicate? Yeah.
variance here between cluster.
Yes.
Okay. All right. Let's go over the variable m. M is what? M is all data centroid, or the mean of the data, which is this point. So the mean is always the same, right? So all data variance is just the sum of all data points, and this is just the regular variance equation, right? X minus mean square divided by n minus 1, right? This is a typical variance equation. We can try to compute the variance in a different way. What if, for here, right, this is a cluster, right? Instead of computing the variance according to each point in the cluster, right? We use the centroid instead. We say, okay, we're going to represent this cluster using the centroid, right? If we,
Yes.
yeah,
No,
so
I'm sorry. I'm confused about like what does the physical meaning of the variance, like is having high variance like indicate something about our model, or like having lower is better? Like what does it like indicate of like our AI model? I understand the mathematics, but like I want to know
okay.
like the
Okay, so the
physical
question is,
meaning.
what's the meaning of variance in this case? Like, why
Yes,
are
yes.
we tracking? Why do we track
Ah,
this
yes.
value in the first place, right?
Right.
Okay. So the variance, in a sense, talks about information in the data. Because let's say that if I have a data that looks like this, everything has a small variance. I might say that, okay, in this data, the feature doesn't give me much information because everything looks the same. But if I have a data that maybe looks like this, right, looks very different, right? Each data point looks very different, right? Has a lot of variance. I may say, oh, okay, in this data, the features is telling something, is telling like is differentiating the people, right? The data in my data set, right? You can think about like let's say that, oh, I have a data set of like students, right? A data set of students, and my data set maybe is only male, female, right? This will give me a small variance, right? Small variance, let's say a variance of like 0.75, right? If I have another data set might be grades of my student, like A, B, C, D, A, right? So this variance may be like 2.5, right? So the variance discuss about like, oh, how much information is in my data set, right? When I talk about information, I talk about like, how can I differentiate the points in my data, right? In male, female, I can only differentiate a student in two ways, right? In the grading, right, I can differentiate the students in a more finer detail, right? And the point
Oh,
of clustering, right? The point of clustering is we want to differentiate the data, right? But we also want to measure how they are different, right? So we want the different cluster to be different, right? But we want the same cluster to be the same as well. So that's why we talk about variance, right? And how this variance is used to explain how they are different and how much information is captured in our clustering. Does that makes more sense?
okay. I see. Thank you.
And yeah, that's a good question. Yeah, very thanks for asking that one. Uh, so this technique, right, has some downside. The one that we discussed before is like here, right? The Mickey Mouse data set doesn't work that well, or if my data is multimodal that looks like this, right? There's two two groups, right? How do we deal with this, right? So we have a solution. which is the second half of this lecture. Which is GMM, right? But before we go to GMM, let's talk about, wait, where's my, oh, this should, another technique in clustering that this should be up here, actually. So another technique that people use in clustering is a technique called DB scan. So in DB scan, instead of clustering based on K, they cluster based on the distance in a radius of epsilon. So let's say, oh, okay, I'm going to look at a distance of 3. So I will look at cluster within the 3-point radius. Right. So this is a DB scan. So you input like the distance instead of K, and it will try to figure out the K for you instead. Right. So another thing that you need to specify is the minimum number of points. So within this distance, right? So let's say I set to 5. So here, within a distance 3, I have 5 points. So this can be a cluster. But if I have a region where there's only 2 points, which is not enough for 5, this one is considered noise and will get discarded. So this is another technique that people use instead of k-means. All right, so any questions so far before we take a break? Any questions? Okay, there's a question in chat that like, oh, for higher dimensions, would k-means still work? Well, let's first answer this one. For higher dimension, would k-means still work? Well, this thing, right? This thing that I talk about, right? This 1 million dimension, it still work. It just takes a very long time. So when I ran this, it took me days to finish running. Days to finish running. So a workaround for this is to reduce the dimension of your data to something smaller, which is something we will talk about next week. So that's one. All right, and then there's a comment like, I feel that while visualizing higher dimensions, there are many ways to explain, right? So your point on the second one is like, there's no clustering can be subjective, right? I think that's the point of your second question. Clustering can be subjective, which is true. And that's why I mentioned about like, if your goal is about getting insights, right? You can cluster many times. Maybe you cluster with like k=5, right? And you get some insights. You can cluster again using k=10 and you get another insight, right? So you can have multiple insights at the same time, right? If that's what your goal is. But if you want to do something more objective, for example, use like your k-mean, use your k-mean to do some classification tasks. If you have some objective metrics, I think that's where you just use the objective metrics to measure your tasks. Right? Okay, then let's take a quick break. Come back at 30, maybe. And if you have other questions, feel free to just leave it here or like just come chat. All right. Let's continue. So if we have like this kind of data where the data has like different variants, right? Or the data is unimodal, that is, there's like two parts, right, of the data. How would we do it, right? So one way, well, first let's look at an example like, okay, if I have like a data that I want to pretty much like fit some Gaussian, right? Fit some Gaussian to the data. In certain cases, I cannot fit the Gaussian that well. I see there's a difference between the Gaussian and the actual data. So in these cases, people usually model the data using Gaussian mixture model, which is, well, just like the name suggests, it's a mixture of Gaussians. All right, so let's say that I have this purple distribution. This purple distribution can be created by using the red Gaussian and the blue Gaussian combined together. Right. So here my total distribution is a summation of P1. P1 is here, and this is P2. So P1 is this one, Gaussian P2 is this one, and I combine them with some parameter that I combine, right? Or I take 60% from this one, 40% from this one to get this purple shape, right? So I can pretty much model any kind of distribution. So let's say, if I have like the very weird distribution, I can say, it's actually can be created by a lot of Gaussian, a lot of small Gaussians. Right. So this is Gaussian mixture model. And we usually write it as something like this, that is a summation of multiple Gaussian together with some weight parameter, right? That this is like how we combine, right? How we combine the Gaussian together. And this weight here usually sums to 1, right? So that they can be combined into a probability. So if we use these two Gaussians to model these distributions, we notice that the graph, right, looks a lot nicer, right, compared to before, which used like one Gaussian that's like here, right, very bad, right? But this one looks nice. So we have this, right? Our probability, well, in general, so this is a mixture model, not Gaussian mixture model. So in general, a mixture model is a probability distribution that combines different P, right? Before this is only Gaussian, right? But now before it's only Gaussian, but now if we talk about just general mixture model, it can be anything, right? So it's not only Gaussians anymore, right? So it can be anything here, and we just combine them according to the weights of the mixture. So you can think about this mixture model as like a distribution with some underlying difference. For example, this can be like, oh, a distribution of cat weights, right? Cat weights, a distribution of cat weights, right? A distribution of cat weights can be just like my cats, right? There are maybe like Siamese cats, there are Persian cats, there are like British cats, right? There are many kind of cats, right? And each type of cats has its own distribution, right? So maybe Siamese cat has like a distribution of like, oh, a mean of 5 and variance of 1. Persian cat has a mean of 3, variance of 2, right? Each breed of cat has different distribution. But when I talk about the overall distribution, I can combine all the different breeds together, right? Let's say that, oh, in my data set, I have 70% Siamese and 30% Persian, right? So I combine them into a mixture model, right? So that's the meaning of like mixture model, right? That, oh, in my distribution, there are actually some underlying differentiator, right? Underlying differentiator that can explain like why there are different parts in the distribution. For example, usually when we talk about like a distribution, right? Let's say that, oh, my distribution is Gaussian, right? I usually have a parameter of the Gaussian, let's say mean and variance. And this distribution give me some data points, right? So this is the parameter of the model, and this is the data, right? That we drawn, right? We drawn some samples from the model, right? If we have two Gaussians, right? Two Gaussian, let's say that, oh, this is from Siamese cat, right? This is from Persian cat, right? Persian cat, right? Two cat breeds, right? So I have like, oh, here's some data from the Persian, some data from the Siamese, right? So this is the case where you know the breakdown of the breed, right? But let's say that maybe when you collect the data, you don't know the breed. You just say, oh, okay, give me the cats, right? Give me the cats, and you just measure the cats, but you don't know the breed. But actually, there are two breeds, but you don't know, right? So the data you only see is only this black dots, right? You don't know the color, right? You don't know the color. So the questions now become that, oh, if you have a data like this black dot, can you guess what the mean and variance of the two breeds are, right? So if in this case, right, if you know the color, right, you can say, okay, let's compute the mean and the variance. Let's compute the mean and the variance, right? So you can do that easily. But in this case, you don't know the breakdown, right? You don't know the breakdown. how do you compute the mean and the variance if you only see the data without all the information? Right. So this is the goal that we will try to work around in this lecture, right? So we have some data like this, right? We have some data like this. We have some information, which is the type of cat that is missing, right? This missing data is called latent variables. Right? Latent variable is the data that is unknown to us, right? The type of cat, whether it's red or blue, right? We don't know, but we only know that, okay, there's this data. We don't know the breakdown. Can we estimate the breakdown? Right? That's the goal of what we're trying to do in this lecture. So in this case, we have to estimate this one, and we also have to estimate this one as well. Right. So now our problem is slightly harder because now we have two things to estimate. Another thing that some of you might be curious since last time. So last time, I usually use this notation. That is, I use like a semicolon, right? X semicolon zeta. How is it different from X given zeta? So when we write like probability distribution, right? X, Y, right? We usually, these variables are random variables, right? Random variables. So when I write it like this, it means that, oh, I'm treating zeta as a random variable, right? But if I write it like this, it means that, oh, I'm treating zeta as some fixed parameter, as in not random, but it's unknown. Right? There's a difference between random and fixed, right? And there's a difference between known and unknown, right? And this notation just say, okay, on the back of this, right, there are fixed value things, right? We're not viewing them as random variables anymore. But this thing can be a parameter of the function. Let's say that, oh, x is binary, right? Binary, then maybe this is like the probability of head, right? Probability of x equal head given not where zeta, right? And this is like, oh, the probability is zeta, where zeta is probability of being head, right? So this is just like, okay, we're going to use zeta as some fixed unknown variable, but it's not random, right? So there's a difference in the notation that is somewhat subtle. But if you're this confuse you a lot, I recommend that maybe just treat this as another given is also okay. But if you want to be exact, right, there's a difference. Okay, so now let's talk about how we can this setting where we have some data and we want to estimate the parameter while we have some unknown things, right? So our task is, let's say we observe some data, right? And we know that this data come from Gaussian mixture, right? Comes from some Gaussian mixture where each mixture means like a different kind of cat, right? So this X1 maybe comes from Siamese, right? This X2 is also Siamese, XN maybe Persian, right? But this thing we don't know, right? We don't know. We only see maybe the weight of the cats, right? We don't know the breed. But when we modeling, right? We are like going to model like, oh, what's the Gaussian of the Siamese? What's the Gaussian of the Persian? Right? We want to model that. So we have some unknown variables. This K is just, okay, this K is just a value that, oh, K1 is Siamese, K2 is Persian. This is the thing that we don't know from K possibilities, right? From K possibilities. And let's give them some parameters. So we have the probability of coming from class 1. Probability of coming from class 1 is phi 1. Probability of coming from class 2 is phi 2. Right? So probability that data is from class 2. Right? Class 2. So if I want to estimate the parameters, right? Just like last time, if I want to estimate a parameter of probability distribution, I can use maximum likelihood. So I say, okay, what's the log likelihood of the data? So okay, so log, right? Log of the sum, because it used to be the product and I take the log, it becomes a sum of log. Okay. And the data point, right? Each data point here. So each data point and the parameters, right? The parameters. I can break this down. Oh, actually, this is wrong. It's here. X of n. So breaking this down, like this probability, I just plug in this term, right? This term here, just plug in this term. I got this one. So it becomes this, right? So the number of data points, and this is number of mixtures, right? Or the different kind of cats that I have. So if we want to solve this, right? What do we want to do? We want to maximize this term, right? Maximize. So how do we maximize? We differentiate, right? We differentiate. So if we try to differentiate this, we're like, okay, the summation, we can put a differentiate in, right? And we differentiate the log, right? How do we differentiate the log? It becomes 1 over this thing, right? 1 over this thing. The problem is there's a sum here. So this is new this time. Before we don't have this. That's why in the previous class, we can differentiate this very easily. But now we have this term. This, if you want to solve this is very hard to differentiate. All right. Okay, so this is hard. All right, this is hard. Just like in k-means, when we say, okay, if we don't have any starting cluster, it's very hard task. What do? We say, okay, let's assume we have something, right? Let's assume we have something. So if you assume that these k are known, right? If you assume k to be known, you can actually differentiate this term. And I won't show you the math, but if you want to look at the math, look at the lecture notes. But this is the output of the differentiation. I'll just go over what the equation means. So if we assume that we know all the case, like we know that, oh, cat number 1 is Siamese, cat number 2 is Persian, cat number 3 is Siamese. If we know this maximization will give you this solution. So what is this again? This is probability of being class J, right? Probability of being class J. This thing is an indicator function. So this function will equal 1 if the condition is met. So here, this function is 1 if the n cat is from class J. Right, so let's say that, oh, I have K1 is class 1, K2 is class 3, K3 is class 1, right? So if I compute phi of 1, I will have a summation of 1 plus 0 plus 1 plus ... from 1 from here, 1 from here, right? So this is the indicator function. It's just a shorthand. It's just a shorthand for counting, right? So this is just average of counts for class J, right? Or the ratio of the how many class J there are, right? Makes sense, right? So this is a prop of being class J, and we just count how many there are, right? Makes sense. What about this? This is the mean of class J. How do we compute the mean of class J? So this is X, right? So usually when we compute the mean, it's like a sum of X n, right? So this is a regular mean computation. We have this indicator function in front, right? So this selects only class J, right? Select only class J. If it's not class J, we just don't add it, right? It becomes 0. If it's class J, we just average it, right? So this is just a very convoluted equation for saying, oh, take all the class J and average it. The same thing, the variance is say, oh, take all the class J and find the variance, right? So if you know K, everything is pretty much business as usual, right? Just more scary math. But the problem is we don't know K, right? In this setting, we don't know K. So what we're going to do is very similar to K-means. That is, we're going to iterate. Right? We're going to start by like, okay, let's find K. After you find K, you find the rest, and then you repeat the two steps. Just like in K-means, we find the centroid and then assign points, and then find centroid, assign point, find centroid, assign point, right? Go back and forth, right? The same thing, right? This is similar to assign point, right? Assign points. This is similar to finding centroid. This algorithm is called expectation maximization. And this first step here, finding K, is called the expectation step or the E step. And the second step is called maximization step or M step. Okay, so what is this thing, right? What is this EM? So first, I'm not sure if you guys learned this before. Maybe not, but so there's this property called Jensen inequality. So in Jensen inequality, we have a convex function. What's a convex function? It's a function that looks like this. Compared to concave function is what? Like this. A cave, a cave, and usually you just remember it like that. Like a cave is like going down, and convex is just the opposite. So in a convex function, right? If you take 2 points, x1, x2, right? And you find the middle point, let's say some intermediate point between x1, x2, let's say here, right? And then you compute the function value here, and you compare it against the average of the function value, which is here. This one will always be larger than the bottom one because the graph is convex, right? No matter which line you draw, right? No matter which line you draw, this will always be true, right? If this graph looks like this, right? This is always be true, right? No matter which line you draw. So you can remember it as a simple things like, oh, average of the function is larger than the function of the average. Right? Where averaging means like, oh, you do a linear interpolation between the values. right? So this is called Jensen's inequality. So this is the proper definition, right? Let some function be convex along some interval. And in this example, we only have 2 points, right? But we can have multiple points, which is a linear combination. So we have like linear combination of multiple points. The same thing still apply. That is, the function of the average is smaller than the average of the function. This is for convex, right? What if f is concave? Well, if your graph look like this, right? How the line behave is just you flip the inequality, right? You flip that is like, oh, the inequality will be this way. And this here, since W here can be like a probability, a probability value. This W can be probability value. You can write this as expectation of X as well. So function of expectation of X is smaller than the expectation of Fx. It's the same thing. All right. So now coming back to our equation here, right? Our equation here, we have this equation which we pretty much say, oh, we are stuck because we cannot differentiate log of sum. Right? Log of sum is hard to differentiate. So what we're going to do is we're going to apply Jensen inequality to help us so that we can maybe differentiate this term, right? So how do we do, right? So from here, log of sum, right? So this is the log of sum that we're having trouble with, right? So here, let's say that, okay, I'm going to define a new function. So let's define qk. So qk be some distribution over k. So it's a probability distribution, something, right? I'm not assuming anything. It's just, I just say, okay, it's a distribution over k. That means it is more than 0 and it's sum to 1, right? And what I'm going to do is, okay, I sum over k here, p of x, k, theta, and I say, okay, let's multiply it and divide it. So it's still equal, right? Multiply and divide, right? And this is the summation, right? So let's just group it. Let's just group it. Just grouping, right? Just grouping. And in this form, right, we notice something. First, log is log convex or concave. Log is a concave function. right? Uh, so we have a function now, right? A function and a sum, right? A sum of W, right? And X, right? X. So if I apply Jensen inequality, what will happen? So this thing is for convex function, right? So for concave, it becomes the other way, right? It's the other way. And I get a sum of K log, I mean Q K and log of P X K zeta Q K. Right. So what I just did is just, I find a lower bound, right? So this is a lower bound of what I want to, what I want, right? So what I want the top one, but it's hard, right? It's hard. I find a lower bound instead. And what do I want to do with the top one? I want to maximize it. Right? I want to maximize the top one. But now I have a lower bound, which is a sum of log, right? A sum of log. So one strategy that I can do, one strategy that I can do is that, maybe if I maximize the lower bound, right, I can push the top one as well. Right? It's not a guarantee, but at least it's better than nothing. Right? I can push the lower bound. Right? So I have like, maybe I have this is the log sum, right? Log sum. And I have the lower bound, which is the sum of log. Right? If I push this up, in a sense, I'm pushing the green thing up as well. Right? And I can differentiate sum of log. Right? Right? Okay, I can push, I can, so maybe I can work with this. Right? I can work with this lower term. Right? This is called evidence lower bound or elbow. Right? This term here is called evidence lower bound. Okay, so now, so this is a lower bound, right? If I can make this, so a lower bound can have like this epsilon difference, right, between the function and the lower bound. My goal here is that, I want to make this lower bound very small so that when I push the lower bound up, right, the top one will also go up farther as well, right? If you notice here, right, this is greater or equal to, right? So the question is, wait, when does this become equal to? When does this inequality becomes just equal, right? So coming back to Jensen, right? When is Jensen inequality tight? Or when does like this become equal? If we look at this graph, when do this become equal? Yeah, your friend here say, it's only equal when x1 equal x2. Basically, you're like, okay, I'm using the same point, and then the difference is zero. Right? That's the only case where Jensen inequality becomes equality. So if the function is strictly convex, then this is tight if and only if all x are equal, or in some sense, the expectation of x is equal to x. That is like there's no expectation. It's just the same thing. That is, x is always a constant. Right? X is always a constant. So if this is true, then that is like our random variable is just a single variable. Our random variable is not really random. Right? It's only one value. So how, right? How? So we're saying like, oh, okay, we want to have this, right? Have this thing. This is our x, right? This is our x. We want this to become a constant, right? We want this to become a constant. Can we do this, right? Can we make this a constant? Turns out that we can, because this q here is something that we just, right? We say, oh, we just conjure it out of thin air, right? We say, oh, let's have some q, right? So we have some room to play with. So let's analyze q a little bit further. We say that, oh, we want this to be true. That is, p over q is some constant, right? And we have some control over q, because q is something that we just create, right? We just create out of thin air. So can we pick some q that makes this true, right? Can we make this true? So if we want to make this true, right, what does this have to be? So if this has to be true, or we say P equals CQ, right? P equals CQ, or in some sense, P is proportional to Q. Right? P is proportional to Q. So, and we know that if we sum Q over K, this will be 1. Right? We know this, we want this to be true, and this has to be true because Q, we say, is a distribution. So with fact 1 and fact 2, right? With these two combined, Q has to be in this form. Q has to be in this form, right? Because this is a constant, right? This is a constant. So Q is proportional to P. And it also will sum to 1. So if this has to be true, right? If we sum K, right? If we sum over K, this will be the variable K will be just like sum out, right? Because we sum all k. And from here, this will be k given x, right, by conditional probability. Right, so this is the form of Q that we want, right? The form of Q that we want. All right. I'll wait a little bit for people to jot down. All right. So we got our algorithm. So let's summarize a little bit. Before we say, okay, we want to maximize this log of sum, which is very hard to differentiate. So we say, okay, let's find the lower bound, right? Which is this, right? We say, okay, let's maximize this instead, right? Maximize this instead. But this thing, right? This thing has this Q, right? This Q, which we just show that, oh, Q has to be this in this form, right? In this P K given X form, so that it's the bound is tight, right? So in our EM algorithm, in our E step, we're going to say that, okay, let's make Q, let's find Q, pretty much find Q, right? This Q is true for a certain theta, right? It's true for a certain theta. After we find Q, right, we can solve this thing. Solving this thing for what? Solving this thing for a new theta. And then we come back here and like, okay, use this theta to find Q, use the Q to find a new theta. We go back and forth, back and forth, back and forth. You can think of this as you're like, oh, you want to maximize something, So this is the maximum point. And you have a dimension that is Q and a dimension that is theta. You're going to like, okay, let's find the best Q. And then, oh, from this Q, let's find the best theta. From this theta, let's find the best Q. From this Q, let's find the best theta. So you're pretty much like optimizing one variable at a time, right? Optimizing one variable at a time while keeping the other one fixed. So will this work, right? Will this work? Let's look at how this will work. So we're going to start at some iteration I. So we have some zeta I. So it's this term, okay? So this is greater than this term according to elbow, right? In the E step, we say, okay, let's pick Q, right? Let's pick Q to be the best possible, right? So now it becomes equal, right? And I color code it to be pink, right? So this blue equals to the pink. And the M step say, okay, we're going to find a better zeta, So this beta zeta I plus 1, which is this red term, is now larger than the pink term, right? Larger or equal, right? So this term here, if I compare it against the same zeta, right? So according to elbow, this should be true, which means that if I compare the green and the blue, the green has a higher probability than the blue. So if I just repeat this 2 steps, I will keep increasing the probability. Some other notes. So in this example of EM, right, or elbow in general, we have this key step here that, oh, we set Q equal to this probability, right? In certain cases, this term is very hard to calculate. So in that case, we will just accept our defeat and pick some K that we can find, right? Any K elbow will still apply, but the inequality might not be that great, right? But it still works, but not so great. In that case, this technique is called variational inference. So this is like the technique that people use in generative AI nowadays, like diffusion model or like variational autoencoders, right? It just stems from the elbow technique, but we don't pick this Q. We pick an easier Q to work with. This is just like a name drop so that anyone who who wants to learn more can just go look at like other literature for this. All right, now back to Gaussian mixtures. All right, so in Gaussian mixture, the E steps talks about finding K, right? Finding K, which is, but in this case, our K is what we call soft label. That is, we say, okay, we're not saying that the first cat is Persian. We're not saying that. We say, okay, the first cat is 30% Siamese, 70% Persian. we say we're going to assign probability that n sample comes from J. It's not like it's not a hard assignment, but it's a soft assignment. That is, we're assigning probabilities to our assignment. Like, oh, okay, it's 70% Persian, it's 30% Siamese, for example. So we're going to find this by computing this term. Right, so we're finding the probability of the n cat be coming from J class according to this probability distribution. This is the E step and the M step, right? Before, if we had hard labels, right? We talked about the indicator function before, the indicator functions here. Since now we are using soft labels, our, right? Before it's 1 or 0, now it's just probability. So to come back to our K-mean, right? The story about K-mean. So if you're like confused, like you can think of GMM, Gaussian mixture model, as like K-mean, but with soft assignments. What do I mean? So here is like the iteration of like Gaussian mixture. So we have like different Gaussian like moving around, just like in K-means, right? We have like the centroid, right? The centroid, but this is like now the mean, right? The mean is moving, just like the centroid is moving, and we have assignments, right? But actually the assignment is soft. So notice how like here is actually probability. It's not like, it's not a hard assignment. Oh, this point is green. This point is blue. It's not. It's like, oh, this point is 30% green, 70% blue. And our shape, right? Our shape can be different, right? Can be different. Before we say, oh, in K-means everything has to be circle of a perfect circle and of the same size, right? But now we are doing Gaussians. So Gaussian can have different means, different variance, is fine. Some notes on Gaussian mixture model. First is, just like K-means, different initialization will lead to different outcomes. So you need to try different starting points, right? And pick the one that you like the best. Another thing is that EM always improve the probability as you iterate, right? If you find that it's not the case, you probably have some bug in your code. Another thing that people might do is that sometimes, let's say, oh, you have like points, right? Points. And you say, okay, here's a cluster and here's another cluster, right? And you say, oh, let's compute the mean and variance of this cluster. What's the variance of this cluster? The variance of this cluster is 0 because there's only one data point. Right. So your calculation will become infinity, which will break things. So usually people will introduce what we call variance floor. That is, we have like, okay, the minimum variance will be 10 to the negative 6, for example, right? Set some very small variance so that you don't get infinity in your calculation. Another thing that is very similar to k-mean is that you have to pick k to do Gaussian mixture. And as you increase k, right? Notice how like, you get pretty much like overfitting, right? Overfitting of your data as you increase k, right? So we need some way to prevent overfitting. So there's a common technique, just like in elbow method, right? In k-mean, there's elbow method. In Gaussians, there's a common method called Bayesian Information Criterion, or BIC. So BIC will plot this value minus 2 log L plus T log N, where this L here, L is the log likelihood value, so the probability term that we have, and T is the number of parameters in the model, like the means, the variance is the parameters, the weights is the parameter. For example, if I have like, I want to do 2 Gaussians in 3 dimensions, right? I have, so the mean is 3 by 1. 3 means variance. The variance is 3 by 3. So this is 9. I have a two Gaussians. So this is 12, 24 parameters plus one from the weights, right? Because I have 2 Gaussian, I have 1 weight, two weight between the two. So I have a total of 25 parameters in this case, like 2 Gaussian in 3 dimensions. Oh, actually it's not 9, it's since this is symmetric, it's 3 and another 3 is 6, 6, 6, 6, 6, 6. So it's 9, 18, 18 plus 1 becomes 19. All right, so this, once you plot this, you want to minimize this value. You pick k that minimizes this value. So this is an example of BAC score, right? So you plot different kind of models, right? Different kind of models. 1 Gaussian, 2 Gaussian, 3 Gaussian, 4 Gaussian, 5 Gaussian, 6 Gaussian, and you try different kinds of Gaussians, like one that is spherical, that is spherical is like, can be any shape. can be tie, that is each different mixture has the same Gaussian, can be diagonal, that is, oh, it's a circle. So different Gaussian type, different components will have different BAC score. And you pick this one that is the lowest. So you will use like a Gaussian of two mixture with full covariance. But just like I said in K-means, this common technique I usually don't recommend. So if you have some goal, right, some goal of your task, just use that goal. All right, so let's talk about some use case of EM. Right, so EM is actually a very versatile technique. For example, you can use it to cluster like image into different parts. Right, so your input is like the RGB value of the image, and your mixture, your K, is just like, oh, the piece, right? This is different K, right? So this is maybe K equals 2 here. This is K equals 1. This is K equals 3, right? So different mixture is a different piece. Right, so this is just more examples. Or another application is like cost estimation. So let's say you have a photo of a person, right? A photo of a person. You want to know the direction that the person is facing. Is he like facing which direction in X, Y, and in Z as well, right? So you're looking at like, oh, the 3D angle of his face. All right, so that's all for today. So we discussed K-mean, which is like a simple technique for clustering data, right? And then we go into like a more powerful model, which is Gaussian mixture model, that can handle more data types, right? And more like works in a probabilistic framework. And there's a homework that pretty much like try playing around with a small data set to do like K-means and do Gaussian mixture on that small data set. Hopefully you get more understanding from trying to implement the technique. All right, that's all. If you have any questions, feel free to chime in, or whatever, feel free to leave.